after after Wednesday? Between R equals the square root of I over A and Dr. Michelson going crazy by putting fluids problems on the seal exam. How many when you saw that problem went, what? Alright, so I'm currently, there is no way that that's graded today. I can't, if anybody expected it to be graded today, my honest goal is to try and just knock this out over the weekend and have you some data on Monday. See, I have an exam in concrete design next Wednesday as well, so I'm doing my best to try and ensure that I don't have two exams to grade at the same time, because that really sucks for me. So I'm going to try and knock this out sooner rather than later. Homework number 3 is still being graded. I'm pretty sure you'll get that one back probably Monday. So, okay. Any questions though? That not about the exam? So I don't even have it graded yet. So. Okay. All right. So I want to sort of recap where we left off because it has been a while. And one more thing. If you're in concrete design, you turned a homework in today. And if you're in steel, I don't have one for you yet. So you don't have any homework this week from my classes. You got the weekend off. I couldn't do anything about that. I said the only thing I can do is put those problems on the exam. That's all I can do. I can see it now. Those folks in concrete design are going to think, how is he going to put stopping sign distance on a concrete roadway? Alright, is that enough? Okay, so we've been talking about bolted connections in here for a while before the exam, so I felt it prudent to sort of go back to square one with bolted connection analysis. So remember that primarily the two types of bolted connections that we as structural engineers have to assess are bearing type connections and then slip critical connections. We will probably get to discussing slip critical connections today. The difference between the two from a design standpoint is that both connections have to be designed according to the limit states of bolt shear and bolt bearing. But slip critical connections have an added check, the check related to the friction resistance that you develop when you pre-tension your bolts. Okay? So, excuse me. For bolt shear capacity, you could compute the capacity if you would like. There's nothing stopping you, but there really isn't a reason. If you go to table 7-1 on page 7-22, all of the bolt shear capacities for commonly available bolts are already computed. It lists capacities for Group A and for Group B bolts, whether or not your threads are included or your threads are excluded, whether or not the bolts are in single shear or in double shear, and based on bolt diameter. So pretty much every variable that you would need to account for is incorporated in table 7.1. So there really isn't a reason to compute bolt shear capacity, just look it up. As for bolt bearing, the easiest way to handle that is to just use the bolt bearing expression. Rn equals 1.2 times the thickness times the ultimate tensile stress times the minimum of either 2 times the bolt diameter or your clear distance L sub C. Now don't forget B values. B values are always 0.75 for bolt bearing. The L sub C value, that's the one that's a little tricky to compute. Well, it's not really tricky, it's just you sort of have to do a little bit of work. So you have an L sub C value for the edge bolts, and L sub C value for the interior bolts. The formulas are pretty easy to derive. Remember, we're using physical dimensions of the hole, so we use a 1/16 of an inch and not an eighth. Now, that's good, great, grand, and wonderful for your strength calculations. If you want your quote-unquote service checks for a bolted connection, basically we're talking about layout requirements, how far apart the bolts are spaced from each other, and how far apart the bolts are from the edges of a given plate. Now, just to be absolutely clear, these bolt spacing and edge distance requirements are completely independent of loading. This is remember what they are for. Remember, why do we have bolt spacing and edge distance requirements? We have minimums to facilitate fabrication. You know, if your bolts get too close together, you can't get a wrench around them. If your bolts get too close to the edge, you can lead to issues with fabrication. Maybe you accidentally tear the plate or what have you. If the bolts get too far apart, generally that means that your plates aren't being adequately forced together, which means there's a gap between your plates, and if there's a gap between the plates, that could lead to the accumulation of water between your connection, and that's no good because that can lead to corrosion. So remember the requirements for bolt, or the reasons for bolt layout requirements. They have nothing to do with load, they have nothing to do with loading direction, it's just the connection in general. We have a minimum spacing, a preferred spacing, and a maximum spacing. Your spacing has to be between the minimum and the maximum. Usually on a homework problem, I will tell you which one to go off of. In design mode, I actually sort of ascribe to the philosophy that the minimum diameter actually works pretty well. If you're using a 3/4 inch bolt, the minimum bolt spacing, if you're using a 3/4 inch bolt, the minimum bolt spacing actually computes out to be 2 inches. So it actually works out as a nice round figure. And 2-inch bolt spacing versus 3-inch bolt spacing, if you can get by with 2-inch bolt spacing, I'd say go with 2, because that's just less steel that you need for connection plates and adjacent elements and so on and so forth. There's nothing wrong with going with 3 times the bolt diameter, but I just take the opinion that if you don't need to waste steel, then don't do it. Minimum edge distances, those are tabulated. There generally is a pattern, but it's not always, it's usually something like your bolt diameter plus about 1/4 inch or something like that, but it can change depending upon your bolt diameter, so just be cognizant of that. And then what we did last time, I think we met, is we went through a full analysis example start to finish. I think hopefully you found that the bolt shear check was really simple. You know, all we had to do for the bolt shear capacity is we said, all right, we have a group A bolt, the threads are excluded, 1 inch in diameter. Is this connection experiencing single shear or double shear? Double shear. So look up the group AX 1 inch diameter double shear capacity. You get a number, I don't remember what it was, but it was pretty high. It was something like 80 kips. 80.1. I can't believe I remember that. So 80.1, so that's 80.1 kips per bolt. 80.1 kips per bolt times the total number of bolts in the connection. That's 6 bolts. Bam, there's your bolt shear capacity. That's pretty simple. So something like 480.6 kips. As for bolt bearing does take a little bit longer. Remember, whenever you do a bolt bearing check, at the very least, you're going to have 2 cases that or at the very worst case scenario, you're going to have 2 cases that you need to analyze. All the plates that are transmitting the load that way, and all the plates that are transmitting the load that way. Now, if you're in connection design mode and you have this ability, you can usually control your connection design where you only need to check one of them, and that'll become a little clear with the next example. But we ended up checking both of these, and I think we found that they were both larger. Or did we find they were both larger than 480? I don't remember. What's that? I don't remember. I'm asking. Did we finish this one? What do you remember?
I thought they were lower.
They were lower?
No, it was 480.6.
That's the bolt shear. I talk about bolt bearing. Okay, so one of them was 457.7. What was the other one? 558. Okay, so one of them governed and one of them didn't. Okay, so ultimately we found that the first case of bolt bearing governed the capacity of this connection. So I think that it was the center plate that was ultimately going to fail in bolt bearing. Am I right on that? Okay, all right. We also did a bolt spacing and bolt edge distance check on the connection, and we found that it was fine. Everything was pretty straightforward. And so there was that. Did anybody have any questions about this example, about example A? Okay. We started to go into bolted connection design. We didn't quite finish it, but we got pretty close mostly towards the way there. What we did is we said, okay, if we have a bearing type bolted connection, the design is pretty straightforward. All you do is determine your load, your factored load, determine the capacity of a single bolt, and then you divide to get the total number of bolts. Then once you got that, lay out your connection according to bolt spacing and edge distance requirements. Once you've got your connection laid out, check the bolt bearing capacity. And that's basically it. So this is the problem that we started to look at. Now, one of the things I mentioned in the last problem was, or when we were discussing the last example, was if you're in design mode, you can usually design your connection to where you only have to check one case of bolt bearing. This is a perfect example of that. In this problem, I have a 12 by 7/8 inch thick plate connected to a 12 by 7/8 inch thick plate. Both of the plates have the same steel grade. They're both A572 grade 50. And so if I use the same dimensions on both plates, I really only have to do one bolt bearing check. I don't need to worry about doing two, because if one meets the requirements, the other one certainly will. So you can usually handle that in a design scenario. Just make sure that you're using the same dimensions and the same grades of steel, right, and you're good. And if you use the same dimensions, but the steel grades are different, just check the one that's weaker, and you know you're going to be fine. So, like I said, you usually have a good bit of control over that in design lane. All right. Here's the problem that we were working on, and let's sort of review where we left off. Now, I apologize, I don't have my Surface with me, so I sort of went on here and I kind of repeated the calcs that we did in class. I tried to make it look as close to what I had on the Surface. So here was the connection we were looking at. Now this this connection was going to be subjected to a dead load of 115 kips and a live load of 160 kips. So the first thing that we needed to do was factor the load. So we factored the load, got a PU of about 394 kips. And then we said, well, it's A572 grade 50 steel, so the FU value is pretty easy to determine. And then we got into designing according to bolt shear. Now these were Group B bolts. The threads were excluded. The bolts were 3/4 inches in diameter. This connection is single shear. Is everybody okay with identifying that as single shear? Just have a plate and a plate, so there's just one shear plane. Look up the capacity, and that capacity is 27.8 kips per bolt. So if the connection is experiencing 394 bolts and VRN is 27.8, divide the two, and that gives you 14 and change. That's how many bolts you need. So just round that up and call it 15 bolts. So we'll do 5 by 3. Sound good? Okay. Now, that's good, great, grand, and wonderful, but that doesn't really address all of our concerns, because we know we have 15 bolts, but we don't really know what to do with them yet. We don't know how to lay them out. We don't know how to arrange them yet. And so the way that we would handle that is to look at bolt spacing and bolt edge distance requirements. So, 1 sec. Okay. So what I'll do is this, just for the sake of keeping this simple, we're going to use minimum bolt spacings. So bless you. Okay. So let's go off of S-min. So S-min is 2 2/3 times the bolt diameter. So to be clear, that is not 2 times 2/3. Okay, that's 2 2/3. So if you want, you can rewrite that as 8/3 times the bolt diameter, which in this problem is 3/4 of an inch, and that comes out to be what? 2 inches, right? The 3's cancel, you got 8/4, so that's 2 inches. Now, what about the minimum edge distance? How do we determine the minimum edge distance? Look it up. And so you look it up in your AISC 15th edition steel construction manual that every single student brought to class, right? Now that was slick. She's like, no, not gonna fly. No. Hey, how's it going? If this is a page that you feel like you need to remember, like where do you find this, it might be worth tabbing. I put a tab just in section J3 in general, but if you want to put a tab here, that's fine as well. Also, I'm just going to give you food for thought. Is this table exactly, the size of the Sistine Chapel? Maybe this table is something you can fit on a formula sheet, so you don't have to look it up.
It's 1 inch.
There we go. What is it?
1 inch.
1 inch. Okay? And so, what's the page?
16.1-132.
And that's table
J3.4.
Okay, so is everybody able to find that? Everybody good? If you're not, this is time. Okay, does everybody have this? I'm going to move on to the next panel. Okay, so here's what I propose then. Okay, we agreed that we needed 15 volts. We have a spacing of 2 inches and an edge distance of 1 inch. So here's my trial connection layout. Okay, now we could do this a number of ways. Now we have 15 volts. 15 volts means I'd like to group those as closely together, so I'd like to do that in sort of a, maybe like a 5-by-3 kind of pattern. And so the way that I'm going to do that is this. Here's my plate. Now, what is the total width of my plate? On this problem? 12 inches. Okay? So what I'm going to do is this. I'm going to say, all right, 1, 2, 3. 1, 2, 3. 1, 2, 1, 2, 3. And so this dimension here is 1 inch. This dimension is 2 inches. 2 inches, 2 inches, 2 inches. And there's my design, okay? Now, I could do maybe 5-by-3. That might be a little tight. I guess it's possible, but I don't know. This connection layout seems to make a little bit more sense. So, as for spacing the bolts out this way, I'm going to space that out evenly. So each of these dimensions here are going to be 3 inches apiece. So they're definitely going to meet the bolt spacing requirement for this dimension. We have a 1 inch edge distance, and we have a 1 inch edge distance and 2 inch bolt spacing interior. So I'm not going to finish this connection design or finish the checks, because now that we have the connection bolt bearing capacity counts are the exact same as we did before. But I am going to lay out some remaining tasks for this connection, okay? Remaining tasks. Okay, so the first task would be to do a bolt bearing check. Okay, now in order to do that, I can help you out with that a little bit, because we know that the bolt spacing is 2 inches. We know that the edge distance is 1 inch. We know that the thickness is 7/8. We know that the FU is 65 KSI, and we know that the bolt diameter is 3/4 of an inch. Okay, so that's pretty easy, because what we can do is we can take these, and we can say, all right, what do we do from here? Well, we know the hole diameter is the bolt diameter plus a 16th. We know that LCE is LE plus DH over 2, right? We know that LCI is S minus DH, right? We have these, right? We can compute 2 dB pretty easily. So everybody's seeing where this is going. And so we can compute an RNE value, an RNI value, and then ultimately compute a BRN. Okay? Now, the only thing we have to make sure that we're clear on is how many edge bolts we have and how many interior bolts we have. So, how many edge bolts do we have on this connection? Number of edge bolts. How many do we have? 3. Remember, this member goes on forever, so we're yanking it over here, so the edge bolts are on the far end. So these 3 bolts are going to be the edge bolts if you're pulling all the way over here. So 3 edge bolts, and how many interior bolts? 12. So if you wanted to compute VRN, how would you do it? Well, you'd take 3 times RNE plus 12 times RNI, multiply the whole thing by V. Alright? I'm not going to go through all this because we did it in the last example, and it is literally just copy-paste. So, just with different numbers. What do you think?
We have to check other limit states.
That's a great question. So, what other checks do we have to do? Well, this is a tension member, so we don't have to do it for the purposes of this problem, but if we were actually evaluating this as a tension member, well, there's still gross section yielding. Net section fracture. Block shear. And then slenderness. So you don't have to do that for the purposes of this problem, and you don't have to do that on any of the homework assignments related to bolted or welded connections, because you've already done it once. I'm not going to make you do it twice. But in real life, this is still a member that's being yanked on. So it's still experiencing axial tension. So because it's experiencing axial tension, it is still subjected to all of these limit states that you need to check. So, does that make sense? Everybody okay with that? All right. Okay. Yes. Okay.
If you were to do slenderness on this plate, are you going to do that funky R value?
Well, it's not that's just how you do it.
Yeah.
All right,
Is that what you do
we'll
this
do
time?
we'll do that together so that it's in everybody's notes.
On the video.
So, the moment of inertia is BH cubed over 12. Remember that there is a strong axis moment of inertia and a weak axis moment of inertia. Okay? So there's 2 ways that we can compute that. The plate is 12 by 7/8. So we could do 12 by 7/8 cubed or 7/8 by 12 cubed. okay? Which one's going to give you the smaller answer? The 12 by 7/8, right? So the moment of inertia is going to be 12 by 7/8 cubed over 12. I don't know what that is.
.66. 0.67.
0.67 inches? No, that's not inches. That's inches to the fourth, right? The area is just going to be, 12 times 7/8. So what is that? 10.5? 10.5 inches squared. The radius of gyration is defined as the square root of I over A, 0.67 inches to the fourth divided by 10.5 inches squared, which equals what? 0.250?
0.253.
How in the world did that calculation take more time than any other calculation
Then
within that problem?
0.9 FYAG?
Still requires you to look up stuff.
Not for that plate. There wasn't anything to look up.
My point. The time to look into the book, grab those values, type it into your
Oh
calculator
my goodness.
is not.
You won't forget it. You won't forget it.
What about WTs?
What's that?
What about WTs?
What do you mean what about?
Like if you're taking a W, you gotta go find like the X bar, but you gotta go to the equivalent WT. How do you do like the moment of inertia?
You don't have to. Look it up. It's right there. The only time you ever need to go through this exercise is for something like a plate. Everything else, all the R values and the I values and the A values are all looked up, or they're all there.
That's pretty good, Dr. Mike. I commend you for that. That was good.
So, L over R has to be less than or equal to 300, then L has to be less than or equal to 300, R, L max is 300, R.
That was just a plate on the exam, or was it shape? What's the plate? Okay.
All right.
Work 9%. This is letter grade.
Let's move on.
I would too.
I haven't even graded it yet, so.
You know dang well 90% is not to get it right.
Oh, goodness. All right. Guys, we got stuff to talk about. I do want to talk to you about this. I want to talk to you about the splice connection. You kind of need to pay attention to this. Okay. Whenever you have a splice, keep in mind what you're doing is you're connecting member A to member B through a plate that is bridging both of them. Okay. So you have member A connected to member B, and you've got this plate bridging them. When you're doing a strength check, you have to ask yourself, well, how would I determine the strength of this connection? Like, let's say bolt shear. Okay? If I'm doing bolt shear, here's what I've got going on. I've got a plate, whatever the diameter is of the bolt. The bolt is in double shear, so I could very easily determine the capacity of a single bolt. But I would then multiply by the number of bolts in order to determine the total capacity of the connection. But the question is how many bolts? Do I multiply by 8 bolts? There's a total amount of 8 bolts in this connection. But do I consider 8? No. I only consider 4. Okay? The reason why is because the bolts are not acting together. Half of the bolts are acting to transfer load this way. The other half of the bolts are transmitting load this way. The easiest way to think about it is what's really going on is you kind of need to cut a section, through the plate, and so what you've really got is this. You've got got a plate here, you've got a plate here, and you've got a plate there, and you've only got 1, 2, 3, 4 bolts to consider. So whenever you see a splice connection like this, when you're doing the analysis, really what you've got to do is cut a section through the middle of it and only consider half of those bolts because they're not all acting together. Half of the bolts are transmitting the load one way, half of the bolts are transmitting the load the other. So don't look at a connection like that and say, well, it's got 8 bolts. It doesn't, okay? It only has 4. Does that make sense? I told you. That's if I put it on the exam. All right. Let's talk about slip critical bolts. Let's talk about slip critical. Okay? Now, a slip critical bolt is a little different. Okay? Up until now, what we've been talking about is, we have plate A, plate B, we stick a bolt in it and we tighten it, but we're not worried about how tight it is. Because when we do our analysis, we're relying on a bearing type connection. So here's the hole, here's the bolt, and so the strength of the connection comes from the bolt literally bearing on the plate. It's literally pushing on the plate. So in that scenario, that's all we're looking at is how strong the bolt is and how strong the plate is. That's it. A slip critical connection is a little different. In a slip critical connection, what you're doing is you're actually making it a point to ensure that you have proper pre-tension on your bolts. Okay? So let's be clear as to what we mean by that. So if you have a plate and you stick a bolt through it, okay, and you start tightening that bolt, what happens to the plates? They stack together, right? The tighter you make the bolt, the harder the plates are going to be stuck together, right? Okay? And so the more that you torque that bolt and the more emphasis you put on that bolt, the more force that you get on the plates this way. So you're developing a normal force between the two plates. Well, remember that whole relationship from physics that if you have a coefficient of static friction and a normal force between two planes, you develop a static frictional force between them? That's basically all this is. When you look at the slip critical capacity of a bolt, it's the normal force times the coefficient of static friction, and then there's a few adjustment factors that go on to that. Now, when do you use slip critical connections? Like when will you use a slip critical connection versus using just a regular old bearing type connection? A very simple answer is any time that an element is subjected to fatigue, any time that you're using an oversized hole or a slotted hole, although we're not going to worry about that for the purposes of our class, and just any other joint in which slip would be detrimental. So I'll go ahead and tell you most regular, beam to column type connections or something like that are not going to be designed as slip critical. But if you have something, let's say in an earthquake scenario, you are probably going to detail that as a slip critical connection. And definitely in bridge land, you're going to detail all of those connections as slip critical. How many of you have ever done any, like work on mechanical work, like on a lawnmower or something like that? If you had, let's say a loose bolt on a lawnmower and you ran that lawnmower, what would happen to the bolt? It'd jingle off, right? It would just fall off. So the same thing's sort of true on a bridge, but instead of the vibrations being so fast, like they would on a lawnmower, just imagine a loose bolt on a bridge after 20, 30 years. It's just going to fall off, right? So in bridge land, we always ensure that those bolts are slip critical to basically ensure that they're going to stay there, that they're not going to go anywhere under that repetitive cyclic loading that happens over its design life. So yeah, I just wanted you to be aware of that. To be fair, slip critical connections, they really aren't that hard to design. I mean, the math isn't really any different than what we've been doing before. But I do want you to understand sort of the pattern of how you would generate a slip critical connection. So, like I said, it's a normal force times a coefficient of static friction. The coefficient of static friction is pretty easy. That's just a lookup. It just depends on the surface of this plate and the surface of that plate. You can look up and figure out what your appropriate coefficient of static friction would be. That's easy. But what about the normal force? If I have a bolt, right? If I have a bolt and I have, let's say, this bolt, and I want to achieve a certain amount of between these two plates. How do I do that? Like, how do I ensure, how do I know that that's how much force I'm going to get? Well, there's really sort of a two-step process. The first step is to get the bolts what we would call snug tight. I'm going to explain what snug tight means here in a second. And then once you get the bolts snug tight, you then need to use a prescribed method in order to achieve the required torque. And there's a number of different ways to do that. But first off, it's a common question that students ask, what's snug tight? Okay? Snug tight is generally the tightness attained with a few hits of an impact wrench, or usually what we would call the full effort of an iron worker with an ordinary spud wrench. So a few hits of an impact wrench or the full impact, that's going to be snug tight. Okay. Now that's not a prescribed pre-tension method of connection, but that's to get it started. Okay. Now how do you get the bolts pre-tension to a predictable, quote unquote, predictable amount of force so that we can actually assume that friction is going to contribute to the strength of the connection? Well, there's a few different ways of doing that. I would argue that the simplest method, it probably is the most labor intensive, but it's the one that's the most common. You've probably seen it used if you've been on DOH sites before, is the turn of the nut method. So how many of you, if you've ever been on a bridge construction site, have seen this? It's a dead giveaway because you'll see these little chalk marks on the bolt and the nut, and they'll mark one end and they'll mark the other, and then they'll turn it so they match. Or maybe you've seen that before. Okay, so that's usually the most common method for achieving a slip critical connection. It is rather labor intensive, so there's a lot of sort of proprietary products that are out there that are intended to make that process less labor intensive, but it's usually more expensive on the materials and tools side. So just something to be aware of. So for those of you that aren't familiar with the turn of the nut method, here's how the turn of the nut method works. What you do is this: once you get the connection snug tight, what you do is you go to your connection and you start marking the bolt, the plate, and the nut in a certain fashion. And these are lookups. So for instance, if you have this diameter bolt and this is your plate thickness, you look it up and it'll say, okay, once you get it snug tight, you do a third of a turn. Okay, so what you'll do is you'll mark the bolt and the plate in one fashion, and then you'll go a third of the turn and then mark the nut. And then what you do is you get a big iron bar or big iron spud wrench or whatnot, and then you turn that, you go effort it and you turn that around so that the bolt has engaged that third of a turn, and you'll see that those marks line up. And so that's sort of a code allowed specified way of achieving that predictable amount of pre-tension. Now I'm sure some of you are like, well, wait a minute, how is this scientific? Like, how are you able to predict this? Well, when we look at the equation here in a little bit, you're going to see how there's a multiplier which accounts for the difference between how much pre-tension you're prescribing and how much you actually get. And usually the way these methods work is that you end up getting far more pre-tension than you actually need. So much so that the code specified multiplier is actually larger than 1. Because on average you get a lot more. That if you use these methods, it's not a matter of undershooting how much pre-tension you need. It's usually the other way around. You're overshooting it. Now, okay, we got time. Okay. As for some of the other methods, one of the other methods is to use some more fancy calibrated wrenches. I think you mentioned this last time using a Skidmore Wilhelm. So whenever you use a calibrated wrench, that calibrated wrench is trying to mechanically induce the proper amount of pre-tension. But in order to use it, you pretty much have to check the wrench every time you start using it. And the way that you check the wrench is you use what's called a Skidmore Wilhelm. A Skidmore Wilhelm, when it comes to installing bolts, is basically a super duper hyper accurate bathroom scale. So the way it works is there's a hole inside and you stick a bolt in, and so you'll use your calibrated wrench to tighten that. And so as you tighten it, it's sort of like a bathroom scale, and it measures how much force that you're applying. And so every time that you go out and you use the wrench, you have to go through and calibrate it to ensure that it's installing the proper amount of pre-tension. So it can be a little bit of a pain to use at the beginning, but then once it's calibrated, you can start, installing pre-tension bolts pretty quickly. Another similar method is kind of the same thing, but is to use what's called twist-off control bolts. So it's kind of the same thing, but the actual bolt that you use is a little bit easier to handle. The bolt itself has, there's a regular everyday nut, but if you look at the end of the bolt, you can kind of see how it's got this like splined end. See this little nub on the end of the bolt? So what happens is this wrench, you can actually tighten the bolt from one end. Like if you've ever tightened bolts, you need a wrench on this end and a wrench on this end to tighten. You actually don't need that with this, because what the wrench does is it actually grabs the bolt here and then it turns the nut at the same time. So you only need a wrench on one end and it turns them both in the opposite direction. And it's also really easy from the inspector's standpoint, because once the bolts are tightened and once the wrench has been calibrated and the bolts are tightened, it actually splines off this chucked in. It sort of chucks it off. So whenever you're looking at a connection, you can see, okay, this one hasn't been tightened yet, but this one has, because that little end has been sort of chucked off after tightening. It just breaks off whenever you hit that required torque. So the inspectors love this, because all you have to do is look at it and go, okay, you're good. Another common method of pre-tensioning, and this also helps a little bit more from the inspector's side, is to use what's called a DTI, direct tension indicator. And a direct tension indicator is basically a super duper hyper fancy washer. So if you look at the washer has these little nubs on the end of it. And so as you tighten the bolt, what happens is from start to finish, those nubs sort of match down. And so you can use these feeler gauges to see, okay, once we've hit that prescribed thickness between the two, we know we've met the required pretension. So there's a number of other methods that can work. There's also these washers that have this sort of like orange putty inside, and so when those nubs mash down, that orange putty kind of squirts out from the bolt. So whenever you're tightening and you see the orange putty, you know you're good. And so there's a lot of different proprietary products out there that go for this. If you didn't have any proprietary products or any fancy wrenches or whatnot, the turn of the nut method would work all the time, but it is a little bit more labor intensive. Okay, everybody good? All right, so like I said, the nominal capacity of a slip critical bolt is exactly what I said it was. You take the coefficient of static friction, the spec refers to that as a mean slip coefficient, but it's the same thing, it's coefficient of static friction. So we take a mu value, we multiply it by a normal force. That normal force is the minimum fastener tension, so it's that T sub B value. And then we have a series of adjustment factors, this D sub U value, this filler plate factor, and the number of slip planes. Now this is not a typo. Usually when you're addressing slip critical connections, this back in the day was essentially a service limit state check. So as a result, we actually use a phi value of 1. So this is one of the few instances where the phi value is a little different than 0.9 or 0.75. Phi is 1 when you're looking at slip critical connections. Now I want to explain what each of these factors are. So like I said, mu is is just your coefficient of static friction, and essentially the code gives you two options. One is basically Class A, regular old, everyday steel. And so Class A surfaces have a mu value of 0.3. Class B surfaces are if you blast clean the steel, like if you really needed to develop additional friction. And if you had blast clean steel, you'd be able to develop more friction, so you'd be able to use a mu value of 0.5. To be honest, I don't think that's used a whole lot. And unless it's otherwise stated, we're always going to assume Class A. So if I don't say anything, it's Class A. You can take that to the bank. D sub U, that's sort of what I was talking about earlier, that multiplier that accounts for the amount of pretension that we specify versus how much we actually get. And on average, using any of these methods that I'm talking about, on average, we usually get about 13% more pretension that we actually specify. Like I said, it's not, usually any of those methods, it's not an issue of not getting enough pretension. We usually end up getting more. In fact, so much more that we adjust this by multiplying our capacity by 1.13. Now, you may know what EOR stands for? Engineer of record. There we go. So if you are the engineer of record on a project and you have a reason for using a different value, you have different test data from your site or something, or it's a really intricate project, the EOR can use a different value if they feel it's justified, and the code does allow you to do that, but that's pretty rare. So just to mention that. T sub B is the minimum specified bolt pretension. Now, before you start tabbing your manual, this is listed in table J3.1, so depending upon the bolt size and whether or not you're looking at a Group A bolt or a Group B bolt, it's a pretty straightforward lookup. It's pretty much equal to 70% of the minimum tensile strength of the bolt, and then that's rounded off to the nearest tip. So it's usually a pretty easy calc. However, a lot of these calcs, you're going to see that a lot of these factors are very similar, and the way that we can handle it is very similar to bolt shear. And I'm going to show you a design guide here in a second. So the only one of these other ones that I think is fairly new is H sub F. So H sub F is a multiplier that accounts for a filler plate. And so this is particularly true in something like a bridge application. A lot of times when you're conducting a bolted splice, when you're connecting member A to member B to try and splice them together, especially in bending, if you're looking at, let's say, connecting a wide flange to another wide flange, a lot of times those wide flanges are not the same size. So if you look, let's say, the wide flange on the left might have thinner flanges than the wide flange on the right. And so when you connect those two, usually what you'll do is you'll include a filler plate so that when you connect them, that this filler plate is sort of making up for that difference in thickness, so the actual splice plate can sit flat on top of them. In most cases, you can probably figure that out with using one filler plate, but if you have like a really weird, really odd plate thicknesses, for instance, if you happen to make up like 3/16 of an inch, so you use one plate that's 1/8 of an inch thick and one plate that's 1/16 of an inch thick. If you ever have multiple filler plates, then you reduce your slip capacity by using a lower HF. The idea is all that steel in the middle means you aren't able to develop as much frictional capacity, and so we handle that with an H sub F. But we're not going to deal with that in here, so we're always going to use H sub F equals 1. You can take that to the bank as well for the purposes of the class. N sub S is a little different as well, but N sub S it's called the number of slip planes, but all that is just the number of shear planes. So N sub S is just the number of pieces, the planes developed between pieces of steel connecting, but that's the exact same thing as the number of shear planes. I know we're running out of time, but I do want to show you something else real quick. If you go to table 7.1, that's the table with the bolt shear capacity. If you literally just turn the page after table 7-1. So you should have table 7-1 tab. If you literally just turn the page, you should have table 7-3 staring right at you, and table 7-3 lists the bolt slip capacity as a function of bolt diameter, and you can see a lot of these parameters are very similar to what we were looking at before. Are we in single slip or double slip? Here's our bolt diameter, it's group A, so there's your capacity. And it's a pretty straightforward calculation. And so, next time we'll do a full-blown slip critical connection design, very similar to what we just did today, and then we'll get into combined loading and interaction. That's all I have, everybody. We'll see you.
Okay.